All right, so welcome back, week 2. We're going to continue today on C programming basics, and then ultimately this week we're going to get into conditionals. Remember that we are online, so if you're watching from home or if you're out here, you can go ahead and go to Piazza and post any questions, and I'll take a look at it periodically. Otherwise, you can go ahead and have discussions back and forth on YouTube. So when we left it off last time, we were looking at the assignment operator. The assignment operator allows you to assign values to your variables. Remember, variables are variables because they can vary. You can put stuff into them. You can put the value 10 into them and then change them later on. You can reset their values. Now, it looks like an algebraic equal sign, but it's not. That's not the interpretation you should have. The interpretation you should have is that you take the thing on the left-hand side, the right-hand side, and you put it into the variable on the left-hand side. The thing on the left-hand side is always a variable. If you try to put something other than a variable on the left-hand side, it will not even compile. Okay? So to demonstrate that, I'm going to show you another tool here. If you just have something quick and dirty that you want to try with C, REPL is an excellent website that you can go to. It's replit.com. And then they've got support for many, many different languages. And it's basically like a stripped down CS50. Now, if you register for it, you can go ahead and save changes to it. But this is not a substitute for CS50 in my opinion. In particular, I don't think that you have too much support for, say, Git and other things at the command line. But you can do something really quick and dirty. For example, you can create an integer variable and set it equal to 10. We'll talk about printf here in a moment, but I'm just going to go ahead and show you that this actually does work by printing out the value 10. And you can see that there's a play button here, just like in the CS50 IDE, where you can actually, similar to, actually you just run it from the command line in the CS50 IDE, and you can see that it has a value 10 here. Later on, you can reset its value. A is equal to 20. And let me go ahead and show you that in fact prints it out as well. So 10, 20. Now, I'm not formatting it well here. I should, of course, be putting in an n-line character so that it's going to one line at a time. Oh, I'm not sure why it's not letting me do that, but whatever. All right. So yeah, it's definitely not a substitute, but there's something wrong there. 10 and 20. Okay? So again, the assignment operator is take the thing on the right-hand side and put it into the variable on the left-hand side. If the thing on the left-hand side is not a variable, for example, you can't do this backwards, right? This will not even compile, right? Say error expression is not assignable. The thing on the left-hand side has to be a single variable in C, okay? But the thing on the right-hand side, you've got a little bit more flexibility. And at this point, I'll go ahead and just go off the notes here. You can reset x to 20, right? So x is equal to 20. Now the value stored in there is 20. But it doesn't have to be just a single value. A single value like 10, 20, those are called literals. It is literally 10. It is literally 20. You can assign it an expression or the value of another variable. Here you can assign the value of a variable to another variable. There we go. So for example, if I've got int a is equal to 10 and int b, I'll just leave it like that. Now remember last time we looked at this first line here, int x, simply declaring a variable named x does not necessarily assign it a value. It could be 0, 99 times out of 100 it will be 0. It's that one time out of 100 that it's going to throw you for a loop. And what's in there? I have no idea. Right? In fact, let's see what it looks like here. If I tried to print out a without assigning its value, what does it do on REPL? All right, it's taken. Oh, there we go. It is 0. But that's just because that's what that particular compiler on that particular system happens to do. You might get completely different behavior if you go over to the CSE server or if you go over to CS50. It is not defined. Not assigning a value. So note. I'll put that in the notes here. Note. Not assigning a value means the variable could have any value, right? Including garbage. There could be just some random value in there. Whatever was left over at that memory location the last time somebody else used it, or last time some other program used it. But now to get down to this this example I was working on here, you can assign the value stored in A to the variable B by simply just doing B is equal to A. It says take the value stored in that variable on the right-hand side and put it into the variable on the left-hand side. Now that does not make them the same variables. It only takes the value that was stored in that variable at the time that this was executed and then puts it into the other value, right? So for example, if I changed it again, if I said that A is equal to now 20, right? B still has the value 10. Why? Because that's what value A had at the time that you assigned the value. B, of course, B will have 10 and A will have 20, right? You can also create use entire expressions, right? So for example, I've got A and B already. Let me go ahead and create one more variable here called C. And I'll assign it a value of, I don't know, 30. All right, there we go. And I can create another variable here, int r is equal to, and I could have an entire expression here. I can multiply things together, I can divide things, I can do whatever I want. For example, I can go negative b plus square root of b times b minus 4 times a, 4 times a times c, all over 2 times a. All right? So does that look familiar? What is that? That's half of the quadratic formula, right? You can't go plus minus in code. You'd have to compute one value, one root value, and then the other root value with the plus, right? But I've got an entire expression in here, and there may be some new symbols. Well, of course, plus, that's not a new symbol. What is that? That's addition. Minus, I'm simply just taking the negative of whatever is stored in B. Star, what is that? That's multiplication, because you don't have that cross symbol anywhere on your QWERTY keyboard. What about this? That's division, right? Because again, you don't have that bar with the 2 dots above and below anywhere on your QWERTY keyboard. So we need to make it an approximation. Now, is that a forward slash or a backslash? Remember, stand to the right and you're leaning forward, you're leaning back, forward slash, backslash, right? And I've got a bunch of parentheses everywhere. Why? Yeah, it's order of operations, right? I can't write it like I would in math, where I can put something up in the numerator, I can put something in the denominator, and then I can draw a line between those two, right? I can't do that in code because I have a plain text file. So I need, if I ever have an expression that needs it, I need to put in parentheses so that that the order of operations takes over. The order of operations should be well known to you. It goes back to grade school. What is it? What's the mnemonic device that you use? PEMDAS. Remember what that stands for? Parentheses, exponents, multiplication, division, addition, and subtraction. That's the order of operations. In other words, you can elevate the order of operations by putting in parentheses wherever you want. Then, of course, exponentiation. Then left to right, it's going to be multiplication, division, addition, and subtraction. So remember that. It also works in code. The reason it works in code is because that's how it works in mathematics. So we just took what we knew from mathematics because we want to make it look familiar, and we put that into code. Right? Note, however, in C, there is no native exponentiation, right? You cannot write something like x raised to the power y or x times y. Some programming languages allow you to do those, but you cannot do that in C. Instead, you would need to use the math library. We've already seen the math library. Well, where do you think the square root came from? SQRT. That's from the math library. sine, cosine. Something else that we used last time, I think, what did we use last time? I forget. We can look up. Right? Maybe we didn't use them, or maybe I didn't. Maybe I didn't actually use it in an expression, but we did talk about the math library. So you cannot use that. Instead, you need to use the math library's Pow function. What do you think Pow stands for? Power, right? It raises x to the power y, and then gives you that. Right? Now, if you just need to raise something squared, right, like I did up here, I didn't use the Pow function for b times b. I could have said b raised to the power 2, but why? It's just multiplication, right? Don't get fancy. Don't use something if you don't need it, if there's something much simpler available to you, okay? All right, so more variable naming tips, all right? So in general, avoid abbreviations, acronyms, etc., unless it is absolutely clear from the context. So if I were doing something financial, right, and I did APR, well, that's probably annual percentage rate, right? If you were in the context, if you were in the zone, if you were thinking about financial stuff and loans and stuff like that, that's probably an okay variable name. It's probably slightly better to name it annual percentage rate, all written out, using lower camel casing. In general, we suggest you use lower camel casing, right, for all of your variables. Where if you've got multiple words that make up your variables, they should all be lowercase except for the first letter of each subsequent word. The first word is all going to be lowercase, and then the second word, you uppercase the first one and uppercase the first letter of every subsequent word. That makes it a little bit more readable. Right? Now, there is an old school way of doing this, or you can use lower underscore casing. And I believe Zybooks, that's an old school way of doing it. Zybooks probably does that. I would not suggest that simply because you want to save your pinky finger, right? What do you have to do if you're always typing underscore, underscore, underscore? Take your pinky finger, put it on the shift key, go all the way up to the hyphen key and hit underscore, right? If you're doing that for every single variable, your pinky finger will eventually fall off. So we suggest using the more modern lower camel casing convention, right? Don't use placeholder names, right? You'll see me do this, but only as a matter of demonstration. What I mean by placeholder names are terrible variable names like foo, bar, baz, or my variable, right? Or variable 1, variable 2. I need another variable. Variable 3, right? Just keep going and going and going like that. Don't do that because eventually you'll declare these variables and then you'll go to use them and you'll think, what the hell did variable 2 stand for, right? Okay, I have to look all the way back up to the top. Okay, now I know what that is. All right, and then you come back all the way back down and you start manipulating things. You lose the forest for the trees, and suddenly you're using variable 3 instead of variable 2, and you don't know what your bug is. Right? You don't know what the error in your program is. Don't do that. Call things what they are. Name things what they model. Right? If it's annual percentage rate, then call it annual percentage rate. If it's number of students, then use that as a variable name. Right? Use descriptive and clear variable names. Right? And that goes for everything else that we'll be using in this course. When you start writing your own functions, write clear function names. Right? We're not there yet, though. All right? In general, be consistent with your program style. That's what we're going to grade on. There are lots of different style guides that you can adopt. You could adopt Google's style guide. You could adopt GNU's style guide. It really doesn't matter. You can make up your own style as long as you stick with it. If you indent things at a certain level using 3 spaces, everything should be indented as using 3 spaces. If you use lower camel casing conventions, then everything should be lower camel casing. If you want to be different and just try the lower underscore casing, you don't care about your pinky falling off, that's fine. Every single variable should use lower underscore casing, right? The consistency is what we're going to be grading on. If it's inconsistent, your first variable is lower camel cased, and your second variable is lower underscore casing, right? We're going to take off for that. So keep that in mind. Consistency is the key. We already looked at all the basic operators. For example, the arithmetic operators. These are pretty straightforward, right? And of course follow the PEMDAS rules. In fact, let's go in the order of PEMDAS. What is it? Multiplication, division, addition, and subtraction. Oops. There. So consider the following. What if I did A plus B times C? Is that the same as A plus B times C? Are those two things, if you were to write that out in mathematics, there's memes all over the place about the gotchas. I forget what it is off the top of my head, but people look at an expression and immediately go left to right and they get it wrong. And then I think that the meme goes that it was in some high school textbook that was automated or whatever, and they didn't even have the correct answer on it, right? So what is the correct? Are these the same? Oh, sorry. Are they the same? Oh, darn it. What am I doing? Because I can't type it. That's just me not being able to type correctly. Now are these the same? All right, thank you. All right. Why? What is the first one? How does the first one get evaluated? B times C first, and then you add A, right, to that result. The second one, because you're using PEMDAS, right, parentheses, you are elevating the A plus B to a higher order of evaluation. So that gets evaluated first, and then the multiplication gets evaluated, right? So these are different. Right? There we go. There's also another operator, another common operator. The division, the integer division operator, excuse me, integer division operator. The percent sign. Now, this is not going to cause you to have a percent. It's not going to take 40 and then convert it to 40%. If you want 40%, then that's 0.4 in mathematics, and it's also going in arithmetic, and it's also going to be 0.4 in your programs. What this does is it provides the remainder. It is also known as the modulus or modulo operator, right? Or simply just mod operation. Its result is the remainder of integer division, right? So for example, suppose that I did just math here, 10 divided by 3. Now normally that would be 3.33333, but we're talking about integer division here. So think back to grade school when you did long division. You didn't, and before your floating point numbers, well, 3 goes into 10 how many times? 3, but then you're left with a remainder of 1, right? So this has a remainder of 1 in integer division. And that's exactly what the operator does. If I did something like 10 mod 3, that results in the value 1. In fact, I'll even code it up here. So that, there we go. So that it's actual code. What if I did, say, 11 mod 3? What does that result in? The value. What's the remainder? 2, right? Because 3 goes into 11 3 times with a remainder of 2 left over. What about, say, 10 mod 2? That results in 0, right? no remainder. And what about 11 mod 2 in 1, right? So those last two, that gives you a way to determine what? If something is odd or even. Now, we haven't gotten to conditionals yet, but we will very shortly. All you have to do is mod out by 2. If the remainder is 0, then it's even. If the remainder is 1, then you know that it's odd. Right? Likewise, if the remainder is 2, then you know that it's not divisible by 3 in the first two results. Right? You can have a remainder of 0, 1, 2, ... up until whatever value you've got that you're modding out by. Okay? There's another pitfall here. Oops. Truncation. So consider the following piece of C code here. I'm just going to go ahead and take 10 and 20. Int A is equal to 10. Int B is equal to 20. Int C is equal to A divided by B. Now, if this were mathematics, what would you say the result is? 10 divided by 20 is 1/2 or 0.5, right? But what's going to happen here in my code? In fact, I'm going to take it and let's go over to REPL, since it's just a small snippet, and let's try to compile it. And we'll print out C. Right? Hopefully this works. 0. Right? It's not 0.5. What happened? Integer divided by integer. Yeah, go ahead. Yeah, it was truncated because it's an integer. 10 divided by 20. Integer divided by integer has to result in an integer. So we'll do 10 divided by 20, and now we've got 0.5. But is 0.5 an integer? Nope. So what happens is we truncate it. We don't round it. We don't round it up. We don't round it down. We don't do any rounding whatsoever. We take the whole number part, which happens to be 0. Then we take the fractional part, everything after the decimal, and throw it away. That's what truncation means, right? If you truncate something, you're cutting off the tail end of it. For example, if somebody's speaking, you can truncate them by cutting them off at the end, right? You're cutting out whatever they were going to say. They've said 0. They were about to say 0.5. You cut them off. You truncated them, and all they said was 0. Right? So it only results in the integer part of it, right? So when you have two integers for arithmetic operations, the result is always an integer. If you divide an integer by an integer, the result will be an integer, but only the whole number part. Right? The fractional part is thrown out entirely and lost. It's not like you can recover that. You can always redo the operation if you want to. This is known as truncation. You can solve this problem using what's called a cast operation, right? Using a casting operation, right? So what I mean by that, or this is called typecasting. I'm going to go ahead and take the same piece of code that we had above, and now I'm going to change it. There, nicely formatted. So I do want the result 0.5. Right? Now, first of all, can I store that into a variable C that's an integer? Can I store 0.5 into an integer? Nope. So my first step here is going to be changing C to a double. Okay. That still will not solve the problem. In fact, I'll show it to you over here. Double. Right? And I'll print it as a double. Again, we'll get to printf here in a second. But it's still 0.00000. It's now a double, but it still is wrong, right? And the reason is, the thing on the right-hand side, it doesn't matter what the result, it only takes the result and puts it into the variable on the left-hand side. It's still an integer divided by an integer. So what I'm going to do is I'm going to temporarily tell C to treat one of these as a double by putting that expression right in front of it. You can do this with both if you want to, but that's more typing. It only needs to be at least one of them. Now what that does is it solves the problem because it says, okay, I will take B and I will temporarily treat it like a floating point number. Not 20, but 20.0. Now 10 divided by 20.0 can be a fractional number, 0.5. And the result is as expected as we wanted. Right? This is called typecasting. It does not change b. b is still an integer. At line 8, b is still a whole number. It is still 20. All I did was temporarily change it to 20.0 for the purposes of that expression. Okay? So let me go ahead and bring this back over to our code. Oops. There we go. Get rid of that, sorry. Anyway, to solve this, we use something like this. Right? This temporarily makes one of the variables, in this case b, into a floating point double for the purposes of the operation. Right? It does not change b. It does not change the type of b. b is still an integer, right? But it results in what we wanted, 0.5. Right? So c is now 0.5. Right? There we go. Other math library functions. Other math stuff. Right? So the math library contains functions for, say, sine, cosine. What else might you want? What's the third one from your trig class? Tan. All right. All right. You kind of see a pattern here, right? They didn't write out sine, S-I-N-E. They didn't write out cosine, C-O-S-I-N-E. They didn't write out tangent, right? Why? Think back to the 70s when C was being developed. In fact, even before that. Computers were not very fast. They were not very large. Nowadays, you think nothing of having an external hard drive that's like 5 terabytes, right? In fact, you can buy a Newegg, like an SSD for with 2 terabytes for maybe $200, $300 SSD. Yes? No? All right. Something like that. Well, you paid by the byte back in the 60s and the 70s. So if you could save 1 byte of information by, instead of writing sine, S-I-N-E, you wrote S-I-N and saved that byte, you did it, right? Because it mattered back then. Doesn't so much matter today, but we still are stuck with this stuff. And since it's familiar, the vast majority of programming languages follow this convention. They don't write out sine, they don't write out cosine, etc. It's just it's not truncated, but it is abbreviated. Another example that we've already seen, SQRT, right? It's much clearer if you had written out square root, but man, back in the 60s, 70s, that would have been expensive, right? So they saved on memory by simply shortening up all their names. Okay. You also have constants that you should use. M underscore pi, I believe I mentioned that before. M underscore e, etc. All right. Note, you may, on some systems, need to use the -lm flag when compiling. I don't believe that you need to do that on the CS50 IDE, so you should be good to go there. Let's go ahead and test it out here. I don't have a program to test it out, come on. There we go. All right, I'll get rid of that for good there. I believe if you do, then it would look something like this. For example, gcc myprogram.c-lm. Now, this is just a quirk. It's just a historic quirk. The -lm is a flag that tells the compiler to link, that's the L, the math library, short for math, right? Not all environments, not all setups require this, but if you do ever have problems compiling with the math library, go back and try to use this flag and see if that fixes the problem. Yeah?
It's not super important, but on the hack you have -ln before my program.
So I believe the CS50 ID would require this because it's Ubuntu. Alternatively, gcc myprogram.c, and like you said, -lm. 99 times out of 100, it doesn't matter. But Ubuntu is kind of persnickety. That's the operating system that CS50 is using in the background. And I've even had problems with it before, with like racking my brains like, okay, the order of the flags matters. And then that suddenly fixes everything. For the vast majority of stuff that we're going to do in this course, we've taken care of that stuff for you. Later on, when you do more complex programs, we provide you with something called a makefile that provides commands on how to build stuff. And we've troubleshot them, and hopefully periodically they'll change their stuff over on CS50. And so I have to go back and I have to change stuff and push it out. My LAs are responsible for troubleshooting that stuff before you get there, though. But if you ever do see a problem like that, please let us know on Piazza. Okay. There are a lot of other functions. The math library has a lot of other functions. How do you know what you can do? So, in the world of alphabet soup here, here's your next acronym, RTM. Right? Read the manual. Right? And now for your purposes, that simply just means Googling it. Right? If I go over to Google, or better yet, DuckDuckGo, I'm going to go ahead and ask, well, what's in that math library? Math.h functions. Right? And this is the manual, right? The tutorials point, whatever brings this up. Okay, there's a cosine. What is a cosine? It's the arc cosine, arc tangent, arc sine, etc. The two-argument arc tangent, which you'll use in your hack later this week. The hyperbolic cosine, right? All those things that you have buttons on your calculator, your TI-82 calculator, that you never actually use, they're all right here for you to not also use them in C. Right? Exp, that's e raised to the power, et cetera, et cetera. Log functions, square root, ceiling, fabs, floor, etc. Okay? RTM, read the manual. Or if you want to be emphatic about it, you RTFM. And I'll let you look up what that means. All right. So basic I/O. I stands for input. O stands for output. So how have you been doing a basic input and output so far? Let's go ahead and let's focus on interactive input first. With interactive input, a program prompts the user to enter a value, or usually one value at a time. Now you can go ahead and hack together a program that says, please enter 4 digits for me. Well, 1, enter, 2, enter, 3, enter, 4, enter. That's really, really error prone because you're not just entering the digits, 1, enter. That enter key is also getting put in as a standard input. So it's best to prompt them for one input. Okay, thank you for that input. Prompt them for the second input, read that second input, and move on, right? The way that this works is that the computer will actually block block the running of the program until the user inputs something, right? So the computer will block the execution of the program until the user has entered their input and hit the enter key. That was a common error that we saw with folks entering, say, their passwords or their GitHub key into the command line. All right, you sit there and you type. You need to tell it, I'm done typing. Right? It's not going to read your mind. Okay, I've typed my password. You need to hit enter to go to say, okay, I'm done typing. Hit enter, and then it reads. Then it processes what you gave it. Okay, that's interactive input. To perform interactive input in C, we'll use, there are lots of ways that you can do this, but the one that we're going to use, at least initially, is scanf, the scanf function. All right, so why is it called scanf? Well, it's scanning the input. You enter in 1,234, and hit enter. What C is going to do is it's going to take that input, which is in kind of what's called an input buffer, and it's going to say, oh, 1, 2, 3, 4, 1,234. All right, and then it processes that value. It's scanning the input and determining what value you actually entered, converting it potentially to a number. And what does the F stand for? It scans for formatted input. The formatting is determined by one of several placeholders. So you've seen them before already, right? There are these mysterious percent signs everywhere, right? It has nothing to do with integer division. For integers, for int types, use %d. What is %d? What is that a placeholder for? It's for a digit, right? Now, actually, it's for decimal. It's for digit. It's kind of weird, right? It's an integer. Why isn't it %i? %i is for something else. I agree that it's weird. They used the wrong letter there, but it is what it is. Right? For double types, use %lf. LF stands for long floating point number. It's just that's what a double is. It's a double precision floating point number. There are floats in C. I don't cover them because they're simply too inaccurate. Why use a float when you can use a double and get double the accuracy? With a float, FLOAT, you can use those in C, but it's only about 7 digits of precision, whereas a double is going to give you about 16 digits of precision. Right? And the last one is the only one that actually makes sense. For char types, use, if it makes sense, then it would match %C. If you need to use, if you prompt the user for an integer, you need to use %d to read in that integer. If you prompt the user for a double and you expect a double back, 10.5, then you need to use %lf. If you're only reading in like a single character, like do you want to continue, yes or no, right? Y or n, then you would use %c for that single character. Right? In general, again, only try to read one input in at a time. Right? Now let's go over here to, well, not that one, but let's go ahead and go to, this one. And let's try to read in a double. Right? So double A. And let's go ahead and try to, here, I'll print it out here. We'll get to that in a second. So I'm going to prompt the user for input. Please enter a floating point number, or a fractional number. All right? That's me prompting the user for input. Now let's actually use scanf. So if I want to read in a double, what was the placeholder again? %lf. And I'll read into A. Okay? Now let's go ahead and run this. All right? Don't worry about that. There was a warning. We'll come back to that in a second. But please enter a fractional number. 10.5. Right. Segmentation fault. What happened? Yeah. Well, say what? Oh no, but scanf should be LF. Printf, we'll get to that in a second. That can be F. Forgot my ampersand. Remember for now that that's just magic. That is passing by reference. In fact, that's what the warning was about. Format specifies types double star. That's a pointer, but the argument was of type double. Unfortunately, it's not being more descriptive here. Maybe giving you a suggestion. Did you forget the ampersand? Yes, I did forget the ampersand. If I run this, let me go ahead and clear this out. Then now the problem has been resolved. 10.5, I read 10.5. Okay. So never forget your ampersand. For now, it is magic, but later we'll understand why you need to use an ampersand for all variables using Scanf. All right, I'll go ahead and make sure that you've got this in the notes if you want it. It's just I'll put it in as a code block here. I should have nice and pretty indentation, right? Consistent indentation. All right, so that's basic input. What if I want, I won't put it in the notes here, but what if I wanted to read an integer instead? Please enter an integer number, or just integer. What's the next change? %d instead. And when I print it out, I'll use %d as well. And if I run this, I get, please enter an integer, 42, my favorite number. There we go. And it works. What if I wanted to do a character instead, or a char? Right? Char A. Please enter a character. Character. I change it to %c, change the output to a %c here, and run it again, and my first initial capital C, and it ran to capital C. If I run that again and I put in a lowercase c, it'll read, they're not the same, they're different letters, right? What would happen if I screwed up and tried to read in a character but print it as a number? I wonder what happens now. 67. Yeah, remember that ASCII text table, right? Capital A starts at 65, so where's B, capital B? 66. Where's capital C? 67. That's why it's printing out 67, right? All characters are nothing more than numbers, and all numbers are nothing more than a bunch of bits, zeros and ones in the computer, okay? All right, so basic output. For us, that's going to mean printf. You can print stuff to the standard output using printf. Now, when we use scanf, we were scanning from the standard, what's called the standard input. The standard input is you sitting there mashing your keyboard. Right? The keyboard is the standard input. The standard output is the terminal or the screen. Right? Now, we've got modern computers here where we've got Windows open everywhere. We've got browsers and stuff like that. We've got different input devices. You can use gestures, right, if you've got it hooked up to a Kinect or something like that. You've got phones now have different inputs, and you know, even with mice, you have clicks and double clicks, and with phones you've got taps and double taps and whatever they call this thing where you move your fingers, zoom and zoom out or whatever, right? But think back again, 40 years ago, you didn't have that stuff. You just had the standard input. The standard input is your QWERTY keyboard. The standard output is, well, whatever happens to be the terminal or the screen at that moment in time. You can use the same formats except for double values. And what I mean by that is, let me go ahead and cut and paste all of these and just rewrite to save on some typing here. For integer values, you still use %d. For double values, however, you can still use a %f if you want to, but it is less error prone to use just a single %f, right? Character types are %c. Now, when you use printf, those placeholders that you put in there will be replaced and formatted with whatever variables you give it, right? So when printing numbers or columns, the placeholders are replaced, right, with the values, with formatted values of the variables you give to printf. Right. So again, let's go ahead and go back over here to REPL, and let me go ahead and put in some more variables here. Int a is equal to 10, double b is equal to 42 or 42.5, and char c is equal to, how do I do a single character? Single quotes, and a capital X. All right, there we go. And if I wanted to print all of those things out at once, I can do that in one single print statement. Printf, the values are %c, what's the placeholder for that floating point number, that double? F. And finally, %c, yay. Right. And then you can tab over if you want to. By the way, how do you do a tab? -T for tab. Otherwise, this is an n-line character right here. Now, if I just did it like this, what's going to happen here? Probably a warning, but it will compile and run. The values are nothing, 0, 8. Yay. Does that look anything like what it should? Right? No. Why? Because I didn't provide the list there. In fact, the warning is telling me about that. Hey, you have this placeholder %c here, but you didn't have any arguments given into that function. Okay, fine. C, B, A. Right. Let's go ahead and try that one more time. In fact, I'll clear this out. No more warnings. But are those the values that we expected? Values are X, 42.5, and then what? What's going on there? An n-line character, yay. Does that look correct to you? No. In fact, what's the n-line? Why is it printing the n-line character? It's printing A as that last placeholder. Remember in the ASCII text table, what's the value of A of 10? The n-line character, right? In fact, if I gave this a value of 65, you would see that it would print capital A, right there. Okay? So let's correct this. If you want, these have to match. The first one, the first placeholder matches with the first variable. The second placeholder matches with the second variable, and so on and so on. So if I want to print these out in the order that I declared them, I would need A, B, and C. And now it'll be as expected. Oops. There we go. That's what I meant to do. There we go. All right. I'll go ahead and put that in the notes so that you have it. But otherwise, order matters. Order matters. The placeholder values matter. Generally, white space around, outside of strings does not matter. But white space inside of strings does matter. You can further format output using modifiers. Right. So what I mean by that is, let's go ahead and look at an example here. So my bank account balance. I'll call this balance instead of B. Say that I've got a whopping $42.50 left in my checking account. Right? Let's go ahead and print it out. I'll use a $sign here, %F dollars in your savings. Right? There we go. And let me get rid of all of this. And I'll print out balance. There we go. So it works. $42.50000 in your savings account. Do you generally see formatting like that when somebody formats currency? No. What should it be? 42.50, and that's it, right? If I only had $42 in my account, right, I would still want to print those two decimal places because that's how you format currency, at least US dollar currency, right? You go over to England. Do they use the decimal place, by the way? The Brits? No, they use what? A weird comma, right? We use commas, but we use commas for every third number, right? To separate ones, thousands, millions, etc. Right? You don't have to do that, by the way, but it makes it so that it's more readable, right? That you have $42 million instead, right? You can't do that in code, by the way. $42 million in my savings account, that's not going to cut it. It will not run. Right? You can't put commas. Commas have a different meaning. But you can do something like this. And you've still got, $42 million and then 6 zeros over here. So what I want to do is I want to change that with modifiers. Generally, you can use %, I'll go into code mode here, %n.m. To format floating point numbers. That is fractional numbers. what the n does, the n specifies the minimum number of columns to print, including the decimal point. The m specifies the number of decimal numbers to the right of the decimal point to print. Okay? So now to understand this, we're just going to look at a couple of examples here. Okay? Well, I don't know what that was, but I don't think it was me. But anyway, let's go ahead and print pi. Remember that the math library has m_pi. So to bring that in, oh, we're good? Okay. Math.h. Let me know if something doesn't appear up there, because it's just mirrored off my screen here. So if something screws up there, yeah, temperature warning, I don't care. It's not mine again, right? So let's print out pi. Pi is %f. Now instead of printing out the balance, I'll go ahead and go with m_pi. The default is what? 3.141593. The default is to print 6 decimal places. So by default, floating point number, I'll just put in 6 decimal. 6 decimal are printed. I want to change that default. So to change that default, we can go ahead and put in that n.m, right? But now, of course, you want to use actual values. So if I said that I wanted to print at least 4 columns with only 3 digits of accuracy, what is this going to print? It printed at least 4 columns, 3.142, right? That first number was a minimum. Print at least 4 columns. Well, there are 5 to print, so it did print at least 4 columns. But the second number here, 3, that specified how many digits to the right of the decimal place to actually print. In this case, only 3. 1, 4, 2. So this prints 3.142. Let's play around with this and see what else we can do. What if I wanted just 4 digits of precision? Right? Remember that pi is what? Let me go ahead and leave in the default here of not using any modifiers at all. And what did it print again? 3.14159.3. All right. So I want you to look at the default here versus 0.3. What did it do to it? It rounded it. That did not change the value of pi. Remember, pi is a constant. It's stored in the math library. You can't change it because it's a preprocessor directive. What it did is, for the purposes of printing, it rounded. If you need to round, you need to do so manually, right? How do I round? C programming round. Right? And what comes up? The round function. I'm RTMing. I am reading the manual. I'm just searching around for what it does, right? And I believe that it's in the it's also in the math library. I think it's in the math library. But there's this round function that does that for you. If 0.5 and above, then half and above, it'll round up. If it's like 0.49999, it'll round down. Okay. And yes, indeed, it is in the math library. But by default, it'll go out to 6 decimal places. If you want to change that, then this version is what? The last version that we just did here, 1.6. And note there that it did not round, because now it's more precise. It's 4 decimals of precision. What if I wanted to get crazy and go with 40 digits of precision here? What's going to happen? Can I represent pi using a double out to 40 decimals? No, remember, you only have 16 digits of precision. So what's it going to end up printing? Are those the actual digits of pi? I have no idea. They're probably not. Anything after the 16th digit is probably just garbage. Right? In fact, I don't know, pi out to 100 digits. In fact, Wolfram Alpha. If you're not familiar with Wolfram Alpha, it's a calculator on steroids. Use it. It's a much better alternative to, say, a TI-89 or whatever you've got. Now, they still require TI-89s in classes probably because they don't have open computer, but whatever. Open computer exams or whatever, but let me just find out what pi is. And there we go. So those are all the digits of pi. Not all of them because, of course, it's infinite, but let's see how accurate this is. 341592653589793, and then that's the first digit that it disagrees at. Everything after this is complete garbage. Right? It's just printing whatever happens to be in the memory location at that moment in time. You asked not for a precise pi, you just asked for a formatted pi. You didn't specify that it actually had to work, right? And you can't unless you bring in the library. How many digits of accuracy was that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Where did we say 16 before? You have about 16 digits of accuracy. Right? So you see this in action. 16 digits of pi with garbage after. Okay? So let's go ahead and take this and modify the other one. Now, what's going to be printed with this example? The interpretation here is I want to print a minimum of 10 columns with 4 digits of accuracy. 4 digits of accuracy plus the decimal place plus the 3, that's only 6. I want a minimum of 10. So how many additional columns are going to be printed? 4. Run this, and we see down here that it prints 1, 2, 3, 4 blanks, and then the number that I asked for. Right? So 4 leading spaces, then 3.1416. Right? So you can play around with that. Why would you want to do something like this? Well, so that you can format money, right, currency properly, so that you can have what looks like columnized things. When you put stuff into a ledger, you always align the decimals so that it's all in one line, right? You can do the same thing with your programs. You can specify that all these digits will be at least 10 columns and accurate only to two digits because it represents a $sign, and they'll all be nicely aligned vertically, right? And that's why you would want to use something like this. Okay, I'll go ahead and make sure that you've got that in your notes as well. Remember, all these notes are pushed to GitHub. When I get home, have my little king, and then while I'm doing that, I'm going to go ahead and push them all out. Right? You can also do other weird stuff with it, like print leading zeros instead. For example, this is just an extra example. My NUID. How many people have an NUID that starts with a 0? All right? You don't have to tell me what it is, but suppose that we had one. Right? Now, is that 0 going to matter for an integer? Nope. If I tried to print this out, let me get rid of all this. Hello, student, %d, and the line. Okay, I don't know why it's doing that, but there we go. Print out NUID. What's this ultimately going to print? Oops. It's wrong. There we go. Semicolon. 3, 4, oh. Okay, I know what's going on here, but let's just go ahead and leave it like that. I'll tell you what happened there in a second. 1, 2, 3, 4, 5, 6, 7. Not those 8 digits of accuracy. So I want 8 columns at minimum. Well, that's fine, but it ends up printing an extra space here instead of the intended 0. You can get leading 0. You can change that space to a 0 by putting 0, 8 instead. All right. Now, what was happening before when I put a 0 in front of it? I was telling C to compile this not as the number 1, 2, 3, 4, not as the integer 1, 2, 3, 4, 5, 6, 7, whatever that happens to be, but to treat it like a hexadecimal number. or something like that. I forget what the leading 0x would be, hexadecimal. It probably does binary or some weird thing like that with this. Right? But I'll make sure that you've got that in the notes too so that you can do that trick. Right? If you ever need to print out an NUID with a leading 0, you can do it with a 0 placeholder. Now there are literally dozens of other placeholders and dozens of other tricks like this that you can use with printf. We could go on for weeks describing all of the stuff that printf can do. It can do conversions from one base to another. It can go from hex to binary or binary to hex or whatever. We're not going to get into it that deeply. I've shown you pretty much everything that you're going to need to use for this class, but understand that it can do a lot more. Not only that, but printf is pretty much universal. If you go over to, say, Java or Python or something like that, the placeholders used and the behavior, it's pretty much in any programming language that you'll encounter. So learning it here can be very, very useful. The last thing we'll talk about today, and we'll also pick it up next time, is non-interactive input. So interactive input, that is using Scanf, makes the program pause and wait for the user to enter in their input. Most programs are not interactive. Most programs, especially command line programs, are not interactive. That's the whole purpose of writing programs to begin with, right? We want to automate things. We don't want somebody sitting there having to type at a computer. Imagine doing that for like a regular old Excel file data entry. Enter in the first value in the ledger. Thank you. Enter in the second value for the ledger. Thank you. Enter in the third value for the ledger, right? You screw up, you got to start all over. No, that's not the way that input actually works. From the command line, you can provide input non-interactively. Right? By using what are called command line arguments. Right? Command line arguments are basically provided when you start the program. CLAs are provided when you start the program. So for example, if I go, traditionally I would go a.out. We do have a question online. How do I find the notes on GitHub? Make sure that you're looking at the weekly retrospectives and make sure that you're looking at the posts on Piazza because I think after the last Wednesday, I posted the link to them. All you need to do is go to the GitHub repo for this course, go under notes, go to your semester, and they're all there. Somebody else can post them as an answer there directly if they want to be a good pal, good peer, and post the actual link up there. Right? All right, notes, and then they're in the folder notes, and then under that the your semester, fall 2021. Right? So CLAs are provided when you enter the program. So hello, 10, 3.5. Right? This example has 4 command line arguments. Right? The first one is always the executable file name. In this case, it would be a.out. Right? So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, and 4. Right? Now, inside your program, you can grab those inputs in a number of ways. Right? Inside of your program, you have access to these arguments using mains. Remember main? What does it look like? Let me just scroll up now. This is a terrible main. It should be int argc char star star argv. Remember I said that was magic before? It's still going to be a little bit of magic, but now we need to understand what they stand for. Argc. Remember we're talking about arguments, right? So arg, argument, C. What do you think C stands for? Not the programming language. It's the count. It's the number of arguments passed, right? So mains argc and argv, right? So argc is the count of the number of arguments provided. Argv, or argument vector, is the vector, or simply just a list or array of arguments. Right. And I'm going to show you how, briefly here, and then we'll reiterate it on Wednesday of how to use this stuff. All right. So in this case, in this particular example, when I gave it 4 command line arguments, right, then argc would have a value of 4. So the advantage there is that if you are expecting the user to input a certain number of arguments, like say 3 arguments, you could say, all right, if they didn't provide all 3 of those arguments, I can quit on them immediately. That's gonna require us to talk about conditionals next time, so we won't do that immediately here. We'll do it on Wednesday. But you can use the argument count to see, was I given the correct number of arguments? If you require 4 and they only gave you 3, or they gave you 50 for whatever reason, they just mashed the keyboard, then you can go ahead and issue an error message and then quit on them. You didn't provide me the number of command line arguments that I expect, so I'm not going to do whatever you asked me to, right? Because a keyboard masher, you can't give them any results. Argv are the actual arguments. Argv sub 0 is the first argument. And as I said above, it is always, which is always, the executable file name. Generally, you don't care about that. Argv sub 1 is the first actual argument that you want. Argv sub 1, right, is the first user-provided argument. And if that's the first user provided argument, what's the next one? Argv sub 2 is the second. Argv sub what? 3 is the third, etc. Right. So you have this argument list, the first one, the second one, the third one, that's provided by the user. Argv sub 0 is always going to be that first command line, that executable file name, usually a.out. But if you compiled your program into myawesomeprogram.exe, right, then the first command line argument would be myawesomeprogram.exe. Right? Again, you generally ignore it. Unfortunately, command CLAs, command line arguments, are all strings. Remember, strings are the double quotes. They're just a sequence of characters, not numbers. Right? To convert arguments into numbers, you can use, here's the first function that we'll use, a to I, or, and then the second one, a to f. What do you think the difference is there? Integers, I, and f, float, right? This converts, the first one converts the argument into an integer, into an integer. The second one converts the argument into a double. There we go. Even though it says f, it still converts it to a double, so don't worry about that. You can use it for floating point numbers if you really want to use floats. I recommend against using floats, even though I think Zybooks uses them all over the place. You're not going to get as accurate of values if you just use exclusively doubles. Right? Now, there are places in which floats are better than doubles. Game programming would be a good one, where you don't need 16 digits of precision to render a single pixel on a screen. You only need 7 digits of precision, and that can lead to faster, more optimized code. Now your TI 3080, it can do a lot more with floats than they can with doubles, because doubles takes double time or whatever the case might be. So game programming and where accuracy doesn't matter that much, then certainly you'd want to use floats. But for this class, I'm going to go ahead and exclusively stick with doubles. Okay. So how does this work? Let's go into a really quick example here. And if I've got argv, argv sub 1, argv sub 2, let's go ahead and convert. Come on, go down. Convert the first user argument to an integer. Well, I've got my int. I need my int. X is equal to a to I. I make a call to that function. I am converting, by the way, a stands for alphanumeric, a string, to an integer. Right? So argv sub 1 is the first argument that the user provided. If I want to convert the second user argument to a double, I would use, well, I need a double first, double y is equal to, and now we would use a to f instead, argv sub 2. And those both would convert over successfully. Now, what if the user didn't provide the correct input? You asked the user, please enter an integer, and they mashed the keyboard and said, hello. Right? What does that look like now? So let's go ahead and show, we'll continue this next time, but let's just go ahead and try it. Int x is equal to a to I of argv sub 1. You know what? At this point, we're not going to be able to try it because I don't remember how to do command line arguments using REPL. Instead, we'll start there next time on the CS50 IDE with a proper environment that I can provide command line arguments as an example. Okay? All right, I'll see you on Wednesday.